everybody, I wanted to take a few minutes and talk to you about getting prepared for lab this week. So lab this week is going to be about solving exponential and logarithmic equations. And when you're solving exponential and logarithmic equations, you really have a two-part strategy that we're going to work with today, a third part that if those two don't work, you'll be able to use starting next week. So if you're trying to solve either a log or an exponential equation, your first option and the thing, probably the easiest step if you can do it, is to make the same base on both sides of the equation. So if you can make it into something like 2 to the x is equal to 2 to some other power, then we can say that the powers are equal, like using the one-to-one property. So that means x is equal to whatever the other two is raised to. The same thing works with logarithmic equations. So if you have, say, the natural log of something on one side of the equation equal to the natural log of some other thing, then whatever those things are have to be the same. So we have this equal to this. So that's your first option, is going and trying to make the same base on both sides. But that's not always successful. So if you can't, then option 2 is to isolate either the exponential part or the log part on one side, and then change forms. So if you're working with an exponential equation to start with, then you'd convert it to logarithmic form. If you're working with a logarithmic equation to start with, you'd convert it to exponential form. So I wanted to do a couple of quick examples just to make sure that you're up and ready to go for lab this week. And the first one we have is 4 to the power of x plus 1 equal to 8 to the power of 2 minus x. So my strategy I'm thinking about is, can I make the same base? Well, 8's not a power of 4. However, they're both a power of 2. So if I were to rewrite the 4 and the 8 as both powers of 2, then I can make the same base and set my exponents equal. So doing that, 4 is 2 squared, and I have that raised to the x plus 1 power. 8 is 2 to the third, and I have that raised to the 2 minus x power. Now remember, rules of exponents say that if you're raising to a power, you multiply. So I want to deal with that multiplication before I drop the bases on these equations. So looking at this, that means that this is 2 to the power, distributing the 2, 2x plus 2, equal to 2 to the power, distributing the 3, 6 minus 3x. Now that I have the same base on both sides, I can set my exponents equal. So 2x plus 2 equal to 6 minus 3x. At some point along the way, you should be down to where you're working with an algebra problem. This is that point. So now I have to solve the resulting algebra problem. Adding 3x to both sides gives me 5x plus 2 equal to 6. Finishing the solution, that means that 5x is equal to 4, x is equal to 4 over 5. Now the same thing is true with logs, so you can make the same base on both sides if it's possible. Now what you can't do, I want to mention, these are all a natural log or a log base e, and the temptation is always there to just drop the logs, but you can't do that unless you have one log on each side of the equal sign equal to each other. So where I have this plus sign in the middle, I need to combine these two logs using rules of logs. So if I have plus, that means we multiply our arguments. So on this side, I have the natural log of x times 3x minus 1. And I still have the natural log of 10 on the right-hand side. Now that I have one single log on each side, I can set my arguments equal. So x times 3x minus 1 is equal to 10. Distributing, it's going to be a quadratic, so 3x squared minus x, and I'm going to bring the 10 over, minus 10 equal to 0. Now I have to work out the factors of this, so I'm going to factor my 3x squared minus x minus 10. So here I'm going to end up, the only things that multiply together to give me 3x squared are going to be 3x and x. Things that multiply together to give me 10, generally speaking 1 and 10 or 2 and 5. Now I need my middle term to be negative, so I can look at, say, if we were to put 2 here, 5 here, I have a positive and negative sign since my end term is negative. So if I do, say, minus 5 plus 2, then my middle term is going to end up being minus 15x plus 2x. So that does not give me negative 1. Going through, if I were to instead take a look at this factor and multiply my 3x by 2, that gives me negative 6x. And if I were to put plus 5 here, I get plus 5x in the middle. So negative 6x plus 5x gives me the negative x that I need, setting both of these factors equal to 0. This one gives me x is equal to 2. This one gives me x is equal to negative 5/3. Now anytime you're working with a log equation, we have to go back and check our domain. So if I'm looking at this solution in particular, that would give me log of a negative number. And remember, the domain of logs is from 0 to infinity. So everything in that argument has to be from 0 not including, to infinity. So this one is not a solution. If I were to look at 2, 2 works fine. So I only have one solution here. Now this is if you can make the same base on both sides, but that's not always the case. So if we look at this next one here, I have 3 times 2 to the x minus 2 equal to 99. I want to look at the bases. If I divide both sides by 3, I get 2 to the x minus 2 equal to 33. 2 is prime, so I can't make it like 4. You can turn it into 2 squared, but 2 is just itself. 33 is not a power of 2, no matter what I do to it, without some tricky fractional powers. So this 33 is not going to be able to be expressed as a 2. So we're looking at option 2 is to isolate and then change forms. So I've got the 2 to a power all by itself on one side, so it's already isolated. So now I'm going to change this to log form. So remember, if I'm working with log form, this is my base. So turning that into log form, I have log base 2 of whatever's on the other side of the equal sign equal to the power. Turning it into log form is a tool in order to break this exponent free. So I have log base 2 of 33 equal to x minus 2. Finishing the solution, I'm going to add 2 to both sides. So x is equal to log base 2 of 33 plus 2. Now this is an exact answer. If I want a decimal approximation, I can put that in my calculator. I may have to use the change of base rule in order to put this piece in my calculator, depending on what calculator model I have. Now, if I'm looking at logs, if I were working with this equation, the first thing I want to do is combine these two logs into one. So using multiplication, I have log of 4x squared, and it's equal to 2. Now the 2 is a number, it's a constant, so it doesn't have a log component involved. So I'm dealing with our second option that we're going to isolate the log on one side, which we've just done, and then switch forms. So if I want to switch forms, remember that the log without a base showing is the common log base 10. So I write this as 10 squared equal to 4x squared. Simplifying, 10 squared is 100 equal to 4x squared. Dividing by 4, I get 25 equal to x squared. Now normally when you have a number equal to a variable squared, we take the square root, we get the plus and minus case. But because of the domain of the log, I can't have a negative 5 in there. So if I were to take the square root of both sides, typically x would be equal to 5 and negative 5, or negative 5 and 5. But this negative 5 is not a solution. So here, x is just equal to 5. Now today and tomorrow in lab, you're going to be working on a focus on biology, which is the zombie apocalypse, and it works with a special exponential model called the logistic growth model. Now if you are looking at this particular function here, this is our logistic growth model. C is called the limiting factor, so it's as big as this function can possibly grow. Unlike a regular exponential function that can grow forever and ever, this logistic growth function is limited by a number. So the curve itself looks something like this. It's pretty unique, and it limits on what's called its carrying capacity. Now the number of people infected with an epidemic or with a virus when an epidemic starts is C over 1 plus A. T is usually a measure of time, and B is the constant representing the number of people infected by each infected person in every unit of time. So today I wanted to talk just about how to solve for T if you have it in this kind of situation. So if I'm looking at this equation here, anytime you have something you're solving for equal to a constant and the thing you're solving for is in fractional form, we want to multiply by the denominator to get rid of our fractional component. So I have 1 plus 40e to the negative 1.5t, and whatever I do to one side I have to do to the other. So here is my factor. Now on the right hand side our denominators cancel, so that was the goal. On the left hand side we're working with this 150 times whatever we have here. Now I'm not going to distribute this in just because, well, you could distribute, or you can divide through by 150, your choice. So if I were to distribute, for example, I'd get 150 plus 40 times 150, quick arithmetic gives me 6,000 e to the negative 1.5t, and it's equal to 380. Subtracting the 150 from both sides gives me 6,000 e to the negative 1.5t equal to 230. I can't make the same base on both sides because I'm working with e and a constant. So I'm going to divide through by 6,000. So e to the negative 1.5t is equal to 230 over 6,000. I'm just going to call it 23 over 600. So I dropped 1 0 top and bottom. Now we're going to use the same strategy. So I want to convert into log form. So remember that e is the natural, is the base that goes with the natural log. So this is the natural log of 23 over 600 equal to the power negative 1.5t. So if we're looking for exact solutions, we're just going to divide through by negative 1.5. So negative 1.5 dividing through on both sides gives us what our t is equal to. So t is equal to the natural log of 23 over 600 divided by negative 1.5. Now this is an exact answer. For applied problem, it's kind of clunky to work with an exact answer, so you'd want to put this into your calculator and get a decimal approximation. Good luck at lab, and I will talk to you again soon.